Alright, so today I want to look at combinations of events. Alright? We'll see how far we can get. We'll have to probably finish this up on Tuesday. Okay? Combinations of events. I want to start out here looking at a Venn diagram. Okay? You guys have used Venn diagrams before with the little circles and they overlap and you put groups of things together. And you show relationships between the groups. Okay? I've got 3 different sets here, and I use the universal set of all the integers from 1 up to 20. Okay? So notice I gave my universal set or my sample space. Those are 2 terms that are similar there. You might hear both of them. Sample space is the same as universal set of 1 to 20. And out of those numbers I formed 3 different sets. Here you see the set of prime numbers. So I have 2, 3, 5, 7, 11, 13, 17, and 19. Those are all the prime numbers less than 20. Okay? Then here we have set E, and those are the multiples of 8 that are less than 20. So we only have 2 elements there, 8 and 16. And then I have this other set, the multiples of 3 less than 20. So I have 3, 6, 9, 12, 15, and 18. And you'll notice here the 3 is actually in both sets at the same time. Okay? Those are in both sets at the same time. Now what would we say, what would we call that part of our Venn diagram? It's where P and T overlap. We would call that the... Wait, what'd you say? Intersection, that's right, okay? That's our intersection. Now notice the notation here. This is P intersect T. Alright? 3 is in the intersection of sets P and T. Alright? Now, there are other intersections here as well. This right here is the intersection of P and E. And this part right here is the intersection of E and T. Notice the notation here. It's this upside down U. Okay? It looks like an upside down U. That's the notation for intersection. Okay?
But the order, does the order matter? Like, can I say, like, E intersect?
The order of those doesn't matter, no. If you say E intersect T or T intersect E, it's talking about the same thing. Okay. That's a great question, though. Right. So you see this notation here. It is a little bit bigger. That's the same notation. That's intersection. When you see the word intersection, think and. It's in this set and it's in that set at the same time. Okay? You could think and, or you could think both if you're just talking about 2 things. Now, the concept I want to look at here is I want to revisit a term that we briefly described at the beginning in our introduction to counting and probability, and that was mutually exclusive events. Okay? Mutually exclusive. We said already earlier that mutually exclusive events are events that are impossible to have happen at the same time. It's impossible for them to occur together. Alright? So looking at our Venn diagram, what are 2 sets that you would say are mutually exclusive?
Prime number and the multiples.
Yeah, very good. The prime numbers and the multiples of 8 are mutually exclusive. Now notice here, in the Venn diagram, that part is empty. Okay? So, let's think of this in terms of probabilities. What is the probability if I pick a random number between 1 and 20? What's the probability that it falls inside that intersection? 0. There is nothing in the intersection. And that, guys, is the mathematical definition of mutually exclusive. There are two things where the probability of picking something in their intersection is 0. Or another way you could say it is that their intersection is the empty set. You could draw the empty set like that. Okay? That's another way of saying that.
Yes.
It's the little curly brackets. Okay? See that? It's the little curly brackets like you would write for a set, but there's nothing inside of it. Okay?
Can I use this one?
A and B we're just using for any two sets. Okay?
So it's just two examples.
Yeah.
So it's
Okay? Yeah, we could say P intersect E is the empty set. Okay? Now, are there any other pairs of sets that are mutually exclusive?
E and T.
Yeah, E and T. Alright, E and T. The intersection here is empty. There's nothing in there. So we would say that's the empty set. Okay? And the probability of picking a random number that is in that intersection is 0. So again, these are pairs of mutually exclusive events.
like if this one, another question, have 3 inside, we should put 1 or put 3.
Well, let's look at that other one, okay? Here's this other one, P intersect T. Alright? P intersect T is not empty. It's got a 3 in it, right?
Oh, put 3.
So what's the probability of picking a random number and getting something in that set? 1 over what? 20. Very good. There's 20 whole different numbers in our sample space. Okay? Does that make sense? Okay? Now, one other thing I wanted to mention here with this one before we go on is this. We're missing something in here. Okay? Notice our sample space and notice the numbers that are in the circles. I'm missing some stuff, right?
What do you mean by sample space?
The sample space is all of the numbers from 1 to 20, right?
Right.
So I'm missing a few of those. Okay? So for this Venn diagram to actually be complete, I would need to include those.
Yeah.
Alright? And they would be outside of any of the circles. Alright? This is our sample space. So let's see, I'm missing the number 1. We're missing 4, 14, and 20. Are we missing another one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yeah. Okay? So now everything is accounted for. Alright? and that Venn diagram is complete. Okay?
So this number is not in the sample space.
They're in the sample space, but they're not in any of those three sets. Okay, so let's take a couple minutes here to consider combined events. We already looked at a kind of combined event where we have an intersection. That's a way of combining events with the word and. We want it to be in this set and in the other one. Okay? The alternative is this. It's the union, where we want it to be one event or the other. Or in other words, we want it to be in one set or the other set. Okay? Now, we have this idea of union here, where we're putting it together. Again, when you see or when you hear the word union, think or. Okay? When you hear union, think or. Or is a much more inclusive kind of a term. Okay? Or is more inclusive. Instead of it having to be in both, it could be in both, or it could be just in one or just in the other. Alright? So, you'll notice here, actually I have a Venn diagram down below. You'll notice here the formula that we have. We have the probability of A union B equals the probability of A plus the probability of B minus the probability of the intersection. Okay? And then if they're mutually exclusive, notice we're not subtracting that intersection. Why don't we have to subtract the intersection if they're mutually exclusive?
Because there's nothing in the intersection.
Very good. There is nothing in the intersection, so the probability of A intersect B is 0, right? There's nothing to subtract anyways. Okay? So if we think about this problem down here, one card is selected from a standard deck of 52 playing cards. What's the probability the card is either a heart or a face card? Okay? Now, this is a great example of one where the Venn diagram is helpful. Okay? Looking at this Venn diagram, are these two sets, the hearts and the face cards, are they mutually exclusive?
No.
No. All right? There's the King of Hearts, Queen of Hearts, and the Jack of Hearts that fall into both sets. So we need to use this first formula. Okay? So the probability of getting a heart or a face card is going to equal the probability of getting a heart plus the probability of getting a face card minus the probability that the card you pick is a heart and a face card. Okay? So let's work this through. What's our probability of getting a heart? What's it? 13 out of 52. Okay? 13 out of 52 cards are hearts. Okay? Which is 1 out of 4. What's the probability that I pick a face card?
1 over 4.
How many face cards are there?
12.
There's 12 total, right? 3 per suit.
Or 12 over 52.
So good, that's 12 over 52. Now our formula says we need to subtract the probability that it's both. So what's that probability?
3 over 52.
Good, 3 over 52. So total, we have a 22 out of 52 chance of getting a heart or a face card. And that's 11 out of 26, which is somewhere around 44%. Okay? Now I want to ask you though, so you understand, why did we subtract the 3 out of 52?
Because
Those are the ones that are in common.
They're the ones in common, they're the ones in the intersection. So why did we leave those out?
they are repeated.
What?
Yes.
They are repeated. Exactly. Notice, I counted those here, and I counted them here. So I've got to subtract one of those, otherwise I count them twice.
Yes.
Okay? Alright, good.
Because
Now, what I want to discuss at this point is the complement principle. Alright? This is why it was important for us to begin with sample space and deal with recognizing all of the possible events in an experiment, or in a situation. Okay? That sample space is all of the possibilities. So, the probability of something happening has to be 100%, okay? It has to be one of those things. So all of those probabilities are going to add up to 100%. And that is why we have what's known as the complement. Alright, if A is one of those events, here's some notation. We read this as A prime, okay? If A is one of the events, then A prime is the complement. You can also read that as not A. Alright? People will read it both ways, okay? So A prime or not A. Okay? Now, what we have just done here is we've divided our situation into two parts that encompass the entire sample space. And as a result, the probability of A happening plus the probability of A not happening has to equal what?
Total, the whole sample space, right?
Yeah, which is?
Probability of not able.
No, we're looking for a number here. What's the?
100%.
100%, there we go. Okay? We have 100% chance of A happening or A not happening. Alright, and if you think about it, that makes sense.
What if you have multiple A's?
Well, that's the thing, then you're not dealing with complements. Okay? To be a complement, you basically have to take your situation and say it either is this or it's not this. If there's a third option, you don't have complements. Okay? Now, the 3 could still add up to 100, but you're not dealing with just something and its complement anymore. Okay? So, using this, we have this probability of a complement. The probability of A prime is 1 minus the probability of A. Okay? So, simple transformation of the equation we just saw. Yes?
If you were to do like A is 87%, would you do 1 minus 0.87 or 1 minus 87?
0.87.
Well, if you're using 1 for 100%, then you would use the 0.87, because 1 is the decimal of 100%.
Okay.
So it doesn't matter as long as you're consistent. If you want to make it 100 minus 87 or 1 minus 0.87,
Okay.
it doesn't matter. Alright, so here's some little examples here. if a drug is meant to cure an infection, it has a probability of working, P of W, 87% of the time. What is P of W prime?
23%.
What is it?
13%.
13%.
Yeah, 13%. The probability of it not working is 1 minus the probability of it working. Okay? So 1 minus the 0.87 would be a 0.13 or 13%. Okay? I don't mind if you give, if it doesn't ask you for a percent specifically, then I don't mind if you give me the decimal or the percent. It doesn't matter either way. Okay? Now, here's another one. What's the probability of rolling 2 dice and getting a sum of at least 4? Alright, this is where you can save yourself some work.
Yeah, you can only do the ones that don't equal 4 or under 4.
Okay, yeah, think about this. The probability of getting something at least 4 means that you've got to add up the probability of getting a 4 plus the probability of getting a 5 plus the probability of getting a 6 plus all the way up to the probability of getting what?
Add probability of getting up to 12.
12, right? That's the highest you can roll with 2 dice.
You can just do probability like 3 and lower,
Okay?
which is 3 and 30 or 112.
Okay. So, let everyone catch up here. Alright, so here we have 9 different probabilities that we would have to figure out and then add them all together. Instead, I could do it as 1 minus the probability of getting less than 4. Okay? You might say, well, I'm still going to have to find out multiple things. You're right, except this time it's 1 minus, now it's just the probability of getting a 3 and the probability of getting a 2, because you can't roll a 1, right? So notice here, I'm cutting down on how much work I have to do. Okay? And as a result, we can then say, okay, well, that's 1 minus, how many different ways can I roll a 2 with my dice? Only one way. I got to get 1 and 1, right? So that's a 1 out of 36. And how many ways can I roll a 3?
2.
2. I can get a 1 and a 2 or a 2 and a 1, right? So that's a 2 out of 36. Okay? So this is 1 minus 3 36ths, which is 33 36ths, or 11 12ths. So my probability of rolling at least a 4 is 11 out of 12. Okay, on average I'm going to roll something 4 or higher 11 out of 12 times I roll the dice. Okay?
Why do they go for 1?
What?
Why do we don't do 1?
Well, because you're rolling 2 dice, right? So you got to at least get a 2. Okay? So the complement is really nice to use when you see something like this where it's talking about at least or no more than or something like that, where you're looking for the probability of a range of values. Okay? So, does this make sense so far? Alright. So, here's another example of a situation. We won't work through it all the way, but the probability of getting at least 2 aces in a 5-card hand, you could get 3 aces or you could get 4 aces. If you get 5 aces, you're cheating, alright? because there aren't 5 aces in the deck. All right, so you can get either 2 aces or 3 aces, or sorry, 2 aces, 3 aces, or 4 aces. Instead of that, I could cut one step out of it and figure out what's the probability of not getting any aces, or what's the probability of just getting 1 ace. Okay? And then I would subtract those
One minus that.
from the 100%. Yeah, 1 minus that.
I think that's the 2 aces.
Okay? So, identifying what the complement is in a given situation is important to be able to do. Okay? Yes?
So it would be 1 minus the probability of 0 and the probability of 1?
Yeah, it would be 1 minus the probability of no aces and the probability of getting 1 ace. Okay? So as we saw before, 52 choose 5 is the total number of 5 card hands you could get. Okay? The probability of not getting any aces would be, you have 4 aces, you don't want any of them, times you have 48 other cards and you want all 5 to come from them, right? The other alternative, here we're adding, we have 4 and we want 1 ace, okay? Which means out of the other 48 cards, I want to choose 4, right? So that right there is my parentheses,
Oh my gosh.
okay? So I just do 1 minus that. Okay?
Why is 4?
Is it 48 and a 4?
Sorry, let me zoom in on that.
Yes.
Yeah. See, notice here, this is no aces. Okay? This is 1 ace. Okay? Notice both hands, they add up to 5 cards out of a total of 52. Okay? 4 and 48 is 52, 0 plus 5 is 5. 4 and 48 is 52, 1 and 4 is 5. So I'm still getting a 5 card hand both times. Okay? If you wanted to, it's not letting me erase. If you wanted to, you could put this as 2 separate fractions. They would both have the same denominator though, so that's why I just put it all together. Okay.
Actually, I want to ask, why do we